My name is Sean Johnson. I work for Path. I'm a software engineer. I run the remote engineering team at Path. How many folks here are remote engineers? Raise your hands. Nice. Go remote engineering. That was about half. That was impressive. So today I'm going to talk to you guys about pattern matching in Clojure. And so how's this going to go? I'd like to talk for a few minutes, maybe 5-10 minutes, about history of pattern matching within programming languages and how we find ourselves here today in 2015 wanting pattern matching within Clojure. And then we're going to go through some how-tos about how it works, how to use it. And then I'm going to share some real-world experiences that I've had using pattern matching for the last few years in Clojure. And the presentation is going to be very code-heavy. So that's good. We're not just going to talk concepts, but we're going to share a lot of code. But it's not going to be live coding. I've seen a lot of live coding here at Clojure West, and I'm not that brave, and I'm just not that guy. So rest assured, though, this will be mostly real-world examples pulled out of my own code and projects, some open source and as well as some closed source code. And we'll have a few examples where we need them for clarity, but I'll try to keep those minimal and brief. So a little bit about the history of pattern matching. So we've got a rich history within programming languages, and it starts all the way back in the 60s with Snowball. And that had a form of pattern matching around strings and something we all in this room would recognize that started to look a little bit like regular expressions. And then in 1972, we got Prolog. And Prolog is a language that has unification at its core. And unification is a kind of extra special, spooky form of pattern matching. And those guys in the 70s, who knows what they were doing. But there was a lot of functional and pattern matching programming language work being done in the 70s and 80s based on a lot of what was happening in Prolog. And we found ourselves in the late 80s with a language, Erlang, which was straight out of the Prolog tradition, but crossed over into commercial use in telecoms initially, and later as a highly concurrent language used on the internet. So there's a rich pattern matching story that spans back from the 60s to today. And it went on into the 90s, and especially in academic languages, we saw more attempts at pattern matching. But where do we stand with Clojure? You notice there's not a Lisp thread through my historical tour there. But let's reset back to those crazy 70s and look at pattern matching within Prolog. And again, that's the kind of pattern matching called unification. And what we do in unification is we just define facts or rules. In this case, we've got two Prolog facts that define what makes a line vertical or what makes it horizontal. And the key thing to look at in these two definitions is just the only thing that changes is x being the same in a vertical line and y being the same in a horizontal line. And you see in the vertical line we have we have y and z for the y-axis, and in the horizontal line we have x and z for the x-axis. So that starts to show how unification works, and we can ask Prolog, is this point vertical? And is this line vertical? And the line with the points 1, 1, and 1, 4 is in fact vertical. And it could tell us when a line isn't vertical. And we haven't, this is our entire program. We haven't done anything imperative. We've just declared what's true about the world, what's logically true. And Prolog is using unification to seek out truth within our data and parrot it back to us. So that was a simple example, and it gets a little more complicated. Here we want to have a function that's arity3, takes two lists, it appends them together. Seems pretty simple. We do it recursively with the first rule saying if we have an empty list and a list, appending them together is just the list that isn't empty. That makes sense. And then we get our first rule here because it has the two parts. It's a rule, and it's a recursive rule. It's recursing back on append, and it's working its way back towards the empty list. And then it's going to, as the recursion unrolls, it's going to accumulate the answer back in L3. And so you don't have to exactly understand how the unification is working there. The point is, Prolog does, and you can ask it questions, and it will tell you that ABC appended to DE is ABCDE, no surprise there. But what is a little surprising is how this is actually happening. Prolog is keeping L3 as an unbound variable as long as possible. And the book that I pulled this example out of doesn't even know how to talk about unification. It says the answer crystallizes out like a snowflake forming around a grain of dust. That's awesome. That is awesome. Poetic and not how we all want to program, I think. So it does spooky things, right? We take that same append implementation and we give it the answer, and it gives us back the question. Like it starts playing Jeopardy with us, right? It tells us what L2 is when we miss that out. So we get this stripping apart behavior when what we were trying to do was write the behavior to append the two things together. It gets even spookier than that. We could start to ask it questions about sort of hypothetical universes. What could L1 and L2 be? And it tells us, well, L1 could be empty and L2 could be the whole string. And then this semicolon says, well, give us more. And it's going to backtrack, unbind some of those variables, and tell us, well, L1 could be A, and then L2 would have to be B, C, D, and E, right? So this is how this two-way pattern matching works in Prolog. So it's two-way. We can have bound things go to unbound, and unbound go to bound. And what makes it quite different than the rest of the pattern matching we're going to be talking about today is we can have unbound match to unbound, and we just keep track of the fact that these two things are going to be the same value eventually, and then Prolog will defer when it actually binds a value there. So if any of this is interesting to you, there's Clojurific ways to explore unification with core logic, and or you could dive right into Learn Prolog. The example we pulled came out of Learn Prolog Now, an online resource. But that's not exactly the type of pattern matching that I want to focus today on when we look at the best practices. It's really the one-way pattern matching where we're going to take something that's bound and match it to something that's unbound, or we're going to take something that's unbound and match it to something that's bound. A little less spooky, a little easier to get our head around. And where I came across this kind of pattern matching and incorporated it mostly into my workflow was with Erlang. That was the first functional language that I used. And Erlang was first implemented within Prolog. That was the language that was implemented. And then it bootstrapped off of Erlang once Erlang was written. And it still has the syntax of Prolog. It looks a lot like Prolog, and although there's alternate syntax now, including Lisp-flavored Erlang, which is kind of interesting for us folks. But what they did is they took Prolog, a language that is not known to be concurrent, didn't have concurrency for a long time, certainly isn't performant enough to be considered soft real-time or known for having very deterministic performance or great uptime. And they said, our goal is to create a language that has all these characteristics. And the only way they were able to do that was these Scandinavian developers, these telecom developers who created Erlang, they pulled unification and backtracking out. So they didn't implement that in their language. What they were left with is something that is quite near and dear to our hearts, which is single assignment and immutability. That's pretty awesome. But also this rich one-way pattern matching story, which is what was left over once they pulled unification out of Prolog. So what does that look like in Erlang? Well, here's some pseudocode that's vaguely Ruby-ish, Python-ish. I made it up. And it's a simple function definition, and we've got a regular old conditional where we're going to go down a few different paths and choose A, B, or C. Everyone in this room can understand this pseudocode. Well, Erlang has a much more declarative and concise and I think appealing implementation of this same code, where we actually take the conditional and bake it in as part of the function definition itself. So if we want expression, if our argument is 0, we get expression A. If our argument is less than 0, we get expression B. Anything else, we get expression C. So you guys can follow. It's the same exact code as the pseudocode, but it's just more declarative, more concise, simpler. Similarly, if we need to have our condition be based on types, we can do that using guard expressions within Erlang and test on the types of the arguments. But pattern matching in Erlang is not just for function definitions, although it's used extensively there, but it's used throughout the language. It's very pervasive. And so I got very used to having pattern matching as just part of how I thought about functional development. So here's an example of a case within Erlang, which is we're just regular old conditional, but this conditional works based off pattern matching. So we're going to pick the type of temperature scale that we're using within the what's called an Erlang tuple, those curly braces, and we're going to also combine that with a guard expression in some cases, and get the right output from this case expression. So if you're interested in any of this, you can learn about Erlang, and I think it's fascinating to see a language that has pattern matching so ingrained in it. But what about us? I mean, we've talked about Prolog, we've talked about Erlang, but what do we get in Clojure for pattern matching? And I'm going to give you a little hint. We have something as a Lisp called macros, and so that's pretty awesome. Even more awesome, more awesomer, is we have superheroes within our community that know how to wield those macros for us. Now we're talking, right? That's my kind of solution. But first, we can get started without any superpowers required. Just right in the Clojure language itself, we're already doing some pattern matching every day, whether we realize it or not. So let's take a look at some of that. The first thing is to get our pattern matching thinking caps in place is to think about destructuring, which we all do, as a mini pattern extraction language. So here's an example. We just have a sequence of person names, and we do some regular destruction. This is Clojure code that we would all run across in our day-to-day use of Clojure. And what we've really done is we've said our data has a certain pattern where we want to extract the first thing out of it, we want to extract the second thing out of it, we want the rest of it, and we want the whole sequence as a fourth thing. So it's regular destructuring, but we're starting to describe the pattern of our data structures and pull elements out. And so we can think about that as pattern extraction. A slightly more realistic example would be a map used to hold configuration information, maybe pulled out of EDN or something. Here's configuration information for a database, and we would use pattern matching, pattern extraction to pull the pieces out so we could use them to connect to the database. Nothing too unusual there. And that destructuring is quite powerful. We've got all sorts of things that help deal with sequential data and associative data structures, to give them default values, and you guys know how destructuring works, I think, but maybe you're not thinking about this as a mini pattern extraction language, and you ought to start thinking about it that way, because the macros that we're going to explore are all built up out of these same concepts and primitives. But beyond destructuring, if you're using multi-methods at all within your Clojure code, then you're using a very, very simple pattern matching macro. So multi-methods are made up of two macros. One of them is def-multi, where you define the multi-method. And the multi-method in Clojure, for those of you who don't know, is just it's Clojure's own kind of functional brand of runtime polymorphism. So you define essentially a functional interface, and then you have multiple implementations of that. And at runtime, you're going to select the right one based on dispatching value, a value of your data that's going to point you to the right function implementation. So that's how multi-methods work. And the highlighted part there is where I'm defining within the multi-method what the dispatching value is going to be. In this case, the value of the exchange key. And so when I call that, at the bottom there, you see order list being invoked with exchange as cripsy. That's going to get pattern matched to the implementation above, where I use the def method macro with cripsy as the dispatch value. Does that make sense? So it's very simple. It's just a simple value, and it stays pretty simple, but it's a form of pattern matching to get some runtime function dispatching. Another example of a macro built into our language that starts to give us some pattern matching capabilities is case, the simple case macro. We've all used the simple case macro. Here's an example. If the count is 0, we're going to get one string. If it's 1, we're going to get another. If it's 2 or 3 or many, you guys know how case works, and you could see the example invocations there. And that's kind of a toy example. Here's an example used in Anger pulled out of my real code where I'm getting back an error that I want to return from the web server. And depending on what exactly happened, why the request wasn't processed, I'm going to return a different kind of response. And so I'm just pattern matching on reason, which is the variable holding my bad thing that happened. And I've got different keywords for each of the different cases, right? So it's very, very simple pattern matching. The problem here with case as a pattern matching macro is sometimes it's too simple. This quote is pulled from the docs for case. And you can see that the test constants, they're not evaluated, right? They must be compile time literals, but you don't need to quote them. But they're just inert. They're just data, right? You can't have an expression, a user-defined function. So what if for your case statement, you want to say, does it contain a certain key? Or is there an inequality? Is it greater than a certain value? Or something more complicated? You can't do that with case. And there's some other macros that help us with conditionals, like con and conp, that get us a little closer to more complicated pattern matching, where we can start to define some expressions and use them. But they're still pretty limited in the same way that the case is limited. So we haven't really, even though we're using macros, and even though we're using some almost proto-pattern matching, we're not really tapping into our superpowers that our superheroes have created for us. So we need some more macros, because macros let us create the language that we want, not the language that we have. And the language I want looks and feels and behaves a little bit more like the Erlang that I first started functional programming with. So I need to tap into those superheroes. And the first one is a gentleman you guys might know. He's Captain America, and it's David Nolan. And the other superhero I'm going to tap into first is Ambrose, and he can't be Captain America because he's not American, but he could be Spider-Man. And so these two guys are going to help me get the language I want out of Clojure. And so these two guys, back in 2011, I think, created CoreMatch. And CoreMatch is a much more powerful pattern matching macro. And this is pulled out of their lips, out of their README. It's an optimized pattern matching library for Clojure. So David's given whole talks on CoreMatch where he's dived into the details on how the sausage is made and why it's so optimized and why it's as efficient as it is. That's not this talk. We're going to talk more about how to use it. The first thing you have to be able to use it is just pull in the dependency into line, or if you're using boot, there's a slightly different way to do that, and then pull it into your namespace. You just need to grab the one thing, the match macro, and you're ready to go. So what does it look like? Here's a toy example, one of the last of the toys. And just so you can get the feel of it, we're matching on an input. It's clear here we think the input's probably a associative structure, a map of some kind. And we're saying if there's a key in this associative data structure and the value of if there's a key, that's the keyword key, and its value is foo, then we want a certain expression. If there's a key and its value is anything, so that underbar, which comes from the Prolog lineage, it means match on anything, but don't bind on it. I'm not going to use the value, but go ahead and match on it. Then we get another expression, and we can use this else keyword to say otherwise, the third expression. So there's CoreMatch. It starts to, at this point, it looks a little bit like case, syntax-wise. And literals match just like the case macro does. If we have a var, it's always going to match, and it's going to be bound. So we can use it in the subsequent expression that we select if everything matches. And the underbar that I mentioned, it's always going to match. And idiomatically, if you use an underbar, you're signaling that you don't care about the binding. So you shouldn't use a variable if you're not going to actually use the variable. It's just you talking to the other programmer saying, we're not going to use this in the expression. And where it starts to get a lot more powerful, though, than case is we have this keyword guard. And guard is going to be a named function of arity1. It could be a name function or an anonymous function of arity1 that's going to return truthy or falsy. And if it returns truthy, that section of the pattern is going to match. And if it returns false, it's, of course, not going to match. So we can start to get pretty complicated patterns out of this this set of functionality. So here's some examples pulled out of real code. Here's an example not using any guard expressions, but that does use quite a few of the other elements. So first thing we do is we use the macro match, and we match on nothing for the first argument and empty for the next two, an empty sequence and an empty map. And if so, we're going to get a certain expression. If the another pattern that we want to match on is if the third thing is nil, if the third thing has a certain key, etc. I think you get the idea. And that in this case, we didn't care to bind and capture any of those values. If we needed, say, the slug and what the value of the category key was, we could capture those with variables and then use them in the expression that we selected. So that's kind of how CoreMatch works. And it has else, as we saw in the prior example. But here's another use of it pulled out of real code, and you start to see where we're pulling in these guard expressions. And the guard expression is working on the argument to the left of it. So the not guard is guarding that argument, that anonymous argument, guarding of absolute ROI. So in this case, we just have one argument, and all the guards are acting on that. But if we had multiple arguments, we could put the guard after the argument that we're trying to have the expression evaluate. So this is great, but what if no pattern matches? That's certainly possible. In all those examples that we showed, where we didn't have an else, it's possible that we just wouldn't have a match at all. And in Erlang, where this thinking maybe originates from, the idea is that you want to let things crash. Let it crash is a mantra in the Erlang community. We don't quite have that mantra within Clojure, but we do want an exception to happen. That's the equivalent of let it crash. That's something unexpected happened. The data doesn't look like we thought it would look like. We don't want to cloud our code with lots of corner cases and edge conditions that we don't expect to ever happen. So we just let the macro throw the illegal argument exception, and it includes some interesting data about what the pattern that couldn't be matched was to help us in debugging. So in this way, pattern matching helps us start to assert about what our data looks like. Everywhere we might put an assertion about the shape of the data, if we're using pattern matching, we've essentially got a built-in assertion. If we just match on the patterns that we expect to see, that we will see if our code is operating properly, and we don't match on the patterns that indicate some unexpected or improper behavior, then essentially we're acting as an assert. So we can deal with those possible patterns, we can ignore the rest, keep the code very clean and declarative. And just to make that concrete, I'll show in the top example, we're matching on a map, and we do expect that the key might not be in there. So we're going to include an else because that's expected, one of the outcomes that we do expect to have happen. If we don't expect that to have happen, it's better not to include the else in our pattern matching. It's not a best practice to always put an else in there, for example. You want to have it fail with the condition of why it failed, why the data is invalid, misformed. So with this CoreMatch macro, do we get Clojure script support? And the answer is yes, we do. We can pull it in, slightly different syntax to pull in a macro, but CoreMatch works within Clojure script, which is great. So we have everything we want and need, I think, out of CoreMatch. We can select cases based on patterns. We can do declarative pattern matching, replacing conditionals in some cases. But one of the things we saw with Erlang was function dispatching based on patterns, and we haven't quite seen that yet. So do we have one more superpower within our group of heroes here? And we do, and that's this Iron Man guy here. And when we pull his Iron Man mask off, we find he's got a second secret identity. I don't know who Dennis is, actually. I have his avatar. He's a wizard, so he's a wizard underneath. And I don't know how to pronounce his real name. If anyone does, they can shout it out, but I'm not going to attempt it. He goes by Dennis, though. So Dennis created a macro in a library called defun, and as is befitting someone who has two secret identities, it's macros all the way down. And so defun is a macro that is wrapping the CoreMatch macro. Okay, so it's a library that's a macro wrapping another library that's a macro. It's awesome. And I didn't have to write it. And so what does this look like? So defun is a pattern matching macro for exactly what we were missing, for defining functions with patterns. So we pull it in just like we would any other library in Langen, for example, and pull it into our namespace. And in Dennis's own words, we get a macro to define Clojure functions with pattern matching just as Erlang or Elixir. Awesome. That's what I wanted. And when we go to use that, you could say, well, we have argument arity overloading, right? We can regularly define a function called say hi and say if we have one argument, do one thing. If we have two arguments, do another thing. Well, that's our kind of our syntax, our syntactic model that we use for defun. So defun has the same kind of thing where we could say if you've got one argument, if you've got two arguments, but we can start to inject patterns in there. And these are the same patterns we saw in CoreMatch. So we have literals like strings like Dennis. We can have keywords like caddy. We can have variables that get bound like name in the third pattern. We can have the underbar to say we don't care about what the value is, match on it, but we don't need it bound. And so it's syntactically it looks just like argument arity overloading. And syntactically, it looks just like CoreMatch. Not surprisingly, everything we just learned applies because it's a wrapper around CoreMatch. So everything we just looked at is how we write these patterns. It's not a new pattern language for us. So let's look at a more realistic example. Let's say we have 2 points, lat and a longe, and we want to know if they're valid or not. We could just write 2 patterns, one pattern for if they're valid, one pattern if they're not. If these guard conditions hold around the lat and around the lon, then it's valid. Otherwise, it's false. And you notice one curious thing maybe. Why did I keep the tuple of 2 underbars for false? Think about it for a minute. The reason is goes back to failing if the data doesn't look like we expect. Right? We expect someone to call a valid geopoint with a lat and a lon. If they called it with something else, say just a lat, then it's not just that it's not a valid geopoint. It's not a geopoint at all, right? So the data is just not what we expected. So we're going to fail with an exception rather than just false. And that's just how I chose to write this particular function to meet the requirements. So what does it look like in Anger? I apologize, the font size went low, but I didn't mean for you to grok all the details here other than to appreciate that this looks just like those CoreMatch examples that we were studying in more detail. It's just in this case, we're actually defining our function in terms of patterns rather than a conditional in terms of patterns. But everything else looks just the same. We're matching on the same kind of literals and the same kind of guard expressions as before. So we've got our 2 pair of macros. We've got pattern matching everywhere we need it. Do we get this in Clojure script? Unfortunately, we don't. We get a GitHub issue instead. So let's get this fixed. I gave this talk once before, and I promised the audience that I would fix this, and I immediately forgot. I hadn't even left the building, and I forgot. But I remembered when I brought these slides back up. So I'm going to promise you guys to get this fixed, and I'll try not to forget. So how well does all this pattern matching work in practice? I want to switch gears a little bit and talk about some of my experiences and some best practices now that you understand how it works. So I've done lots of Erlang and lots of Elixir where pattern matching was used pretty extensively. And then within the Clojure world, I first started to use it incidentally. I added these macros to my toolkit, and when something really jumped out at me as needing pattern matching to be clear and concise and declarative, and to get rid of some conditionals, I would use it. And so I had a couple projects where I kind of incidentally used pattern matching. One of them is open source. You could take a look at that. I then did a project later on where I said, what if I deliberately used pattern matching? What if I used it everywhere that I could? How would my code turn out? If I deliberately thought, should I be using pattern matching here as an actual coding practice? One of the kind of checklist things you go through mentally. And the project that came out of that, post-here.io, you guys could take a look at. And I think it's a great code base. It's not necessarily super idiomatic Clojure because it uses pattern matching rather extensively, but I think it should be more idiomatic than it is. I think Clojure code should look a little bit more like that. And I think it's nice and clean and simple and declarative, and I'm quite happy with how that turned out. So inspired by that, I embarked on 2 other projects where I said, well, what if I used pattern matching maximally? What if I didn't do any other kind of conditional except pattern matching? And so I've got these 2 projects. They're both in progress, and the verdict's still out. I'm not quite as bullish about maximal use of pattern matching. I think it's got diminishing returns if you go completely crazy with it. So I think the sweet spot is to use it deliberately, to consciously think about when you can use pattern matching to make your code more declarative, make your code simpler, remove some conditionals. And I think that's a nice sweet spot for it. And does it hurt anywhere? That's a question I sometimes get is, where shouldn't I use it? And for the most part, it's nice. It does have one problem that I've run into quite a bit in real usage, which is the guard expressions are a bit myopic. What I mean by that is, here's a toy example, but I've got 2 arguments, and I've left off whether this is match or defun because it applies equally to both. But I want to guard on, I want to find out if the intersection between these 2 arguments is empty. And if the intersection is not empty, then I want this pattern to match. Seems reasonable, right? Seems like a pattern we'd like to write. Well, we can't quite write it like this because you see that question mark there. That's not syntax. That's me scratching my head. There's nothing I can put there to refer to the other argument, right? I can guard on McCoy's, or I can guard on Hatfield's, and I can have an expression there, but I can't guard on both and consider them both within the expression. That's just a limitation of those macros as they exist today. There is a workaround, which is that you could pack those arguments up into a tuple. So you just take your Hatfields and McCoys, pack them up into a sequence, and you have one argument called participants that you can then guard on, write your expression as you'd want to look for a non-empty intersection. So that's just something that I find occasionally have to do in my code. Not too often, 1 out of 10 times or so, this will come up and makes the pattern matching code not as simple as I would like it to be. So what are some best practices that I found for applying this? And one of the things you can do is use pattern matching to eliminate any conditionals that are the first expression of a function. And you can also use it to eliminate nesting conditionals. And I'm going to show you one example that hits on both of these at the same time. It's a twofer. So this is some Clojure that we can all grok. I mean, it's not the most complicated thing in the world. It's not immediately apparent either. You have to think about it for a second to figure out what exactly is happening and the fact that there's kind of 3 cases here in this conditional with an embedded conditional. But if we wrote that with defun and pattern matching, I think that Clojure code is a lot more clear. It's immediately visually clear that I've got 3 cases and what I'm doing in each of those 3 cases. So I just think that second set of code reads much nicer and is what I would hope would become more idiomatic Clojure over time. Another best practice for pattern matching is when you've got varied function inputs coming into the same function. So in this case, we've got the third argument is kind of the key argument here. It could be nil. We've got to do one thing. It could be a scalar. We have to do some other set of expressions. It could be sequential. It could be associative. So rather than writing conditionally a function that has complexity to handle this, we just define, like we would in Erlang, we just define the function 4 different ways based on the pattern matching what our incoming arguments are. So this kind of varied function inputs works really well with pattern matching. And this last best practice is my absolute favorite one. I call it the recursive function pattern of pattern matching. And it comes straight out of Erlang, where when you have recursion in Erlang, it's usually made up of 3 or more function definitions all together. And so you have a set of function, one or sometimes more than one set of function definitions that are pattern matching to your start cases or your start case. Then you have 1 or more functions that are doing the work of the recursion, that are progressing towards some end cases. And some end cases where you eventually you need to stop recursing and return a result. And so that pattern of start, work, and end is just how recursion kind of is defined within Erlang. And so what that ends up looking like, I've got the color coding there. We've got one pattern. That's our start case. It happens to be arity 2 going to arity 3. And that's very common in recursion. You've got to initiate and and have your accumulator that you're going to accumulate the result. So you might have a couple arguments or a few arguments coming in. Now you've got to have one or more arguments to accumulate your results as you're recursing. And you better have some end cases, or at least one end case that you're working towards, or your recursion is never going to finish. And these second two patterns match end cases. And having two of them is not so uncommon. One of them is a short circuit pattern. It's saying like there actually isn't any work to do here. We never need to recurse. And one of them is the normal end case of the normal recursion. And then you better have one or more patterns that are actually doing the work of recursing and getting you towards the end state. And that's what's happening there as we sort of are eating a list and accumulating results. So that's very typical pattern matching in Erlang. And this is typical pattern matching based recursion in Erlang. And this is what typical recursion in Clojure looks like. This is the definition of zip map straight out of the Clojure source code. And it's okay. I mean, this is idiomatic. I like it. I can read it and understand it. And it's pretty good. And if we look at who wrote it, I mean, the guy's not a complete bozo. I mean, he knows what he's doing, right? I'm not going to say anything wrong with this code. But everywhere that we have recursion, we really do have this pattern, this hidden pattern of start, work, and end. And if we make it explicit, I think recursion starts to make a little bit more sense for everyone. So where is it here? We do still have a start case, and that's the loop within the function. We come in with two things, keys and values, and we need a third thing. We need to accumulate into the map. That's going to be our end result. So we have this starting pattern that's the start of our loop, and we have a conditional to say, are we done yet? If we're not done, we're going to work towards the done state, and then when we're done, we return the map. Right? So we still have this same pattern of start, work, and end. But this is how recursion typically looks within Clojure. And it's okay, but I think it could be better. And here's my implementation of it with defun and pattern matching. And I think this is just simpler, more declarative, clearer, and I like looking at this code better. It makes more sense to me. So where's our pattern there? We've got 4 patterns, 4 cases. We've got our start case, which coming in as arity2, recursing with arity3 with our initialized map. We've got our 2 end cases. Notice we have 2 here instead of 1. Before, we were kind of hiding the fact that there were actually 2 ways for this to end. We could end with running out of keys, or we could end with running out of values. And I think with this restatement, that fact is much more clear to the reader. And then we've got our case where we're going to work towards the end by working through the keys and the values. So we can compare those two, and I think you guys hopefully agree that the one on the bottom is at least as clear. And once you've looked at it a few times, maybe you'll agree with me that it's more clear than the example on the top. So that's the recursive function matching pattern, for lack of a better word. So let's just restate some of those takeaways. Patterns that I'm suggesting you use, they're not new, they're not scary, they've got a rich history within programming language design. They can lead to simpler and much more declarative code. Please do use CoreMatch and defun. We've been given these superpowers. I hope we all start using them. And there are some best practices you can take away from this as you start to use these libraries and these macros. You can use pattern matching to eliminate those conditionals, especially when they're the first expression of a function or when they're nested. And great for using for dealing with varied function inputs. And then my favorite is that restatement of recursion as the start, work, end pattern. I think that's particularly strong. So I'd like to thank a few people for having me here today. Cognitech put this conference on, and the creators of the libraries and things that we looked at today. And I'd like to open it up for any questions.
So in your zip map example, I'm curious about performance in that particular case. So for example, what does all that matching stuff in the macro expand out to?
Yeah, so you should always take a look, right, when using macros, do a macro expand and take a look. And the code's relatively simple, relatively straightforward. So what I would do is I would encourage you to answer this question. Sorry, I'll restate the question. The question was, what is the performance implication of doing pattern matching? And I'd encourage you to take a look at David Nolan's talk he did back in probably 2011 or 2012 to the New York City Clojure group. It's online. It's about an hour long, and he walks through kind of how the sausage is made and how he builds up kind of truth tables and reorders some of those arguments to get really efficient implementation of pattern matching within CoreMatch. So it's very efficient. It's slower, though. You're trading off developer clarity, right, for runtime performance. Those macros are not going to perform as well as Rich's original recursion implementation. And I'm not trying to suggest that Rich should have written his code like I wrote it, but we're not writing typically things like zip map that are being used by everyone, right, and can stand to have that kind of performance tweaking to them, where you have extremely heavily used code that you need to study and make performance optimizations to. You're probably going to eventually, over time, eliminate some of this pattern matching that you might start with. But you don't want to suffer premature optimization. Majority of the time, our code doesn't ever need to get looked at from a performance perspective, right? We're dealing with relatively small data structures, relatively infrequent usage, and developer clarity, speed of writing the code, speed of people understanding the code is really the bottleneck, not the performance at runtime. But oftentimes, as you start to study, isolate performance bottlenecks and eliminate them, you might eliminate pattern matching in the process. Other questions down here?
Have you seen core.type used to help maybe solve what happens in the default case scenario, or are those basically not really converged?
Yeah, those haven't really converged at this point. Core type came much later, and not too much has happened, I think, to pull those two things together. I think it's an interesting area, and the fact that Ambrose was involved in both could lead those things to come back together in a really powerful. I'd love to see a reimagining of CoreMatch in light of what's happening in core type, but I think core type is still a moving target. Maybe over there.
Erlang comes with TCO baked in, and recursion is pretty natural. And the Clojure world on JVM, we have to take some care ourselves in order to do recursive work. Do these macros change the game in terms of standard recursion?
They don't, right? If you use recur in the macro, you're still ending up with recur in your code, so that doesn't change. And so you're still getting either an error because you're not actually tail recursing, or you're getting the performance of tail recursion. So it doesn't necessarily change the game, because if you write your recursion in the kind of pattern I described there, you're using recur explicitly, and you're getting kind of the tail recur type of behavior. But that's a great point, that Erlang as a language sort of embraces recursion and tail recursion in a way that, with its VM that was created just for Erlang, in a way that we can't with a VM that was actually created for Java that we have. Other questions? Let's see, up there.
This was kind of half-assed by the gentleman up front, but even if core.type isn't something that sort of integrates well, is there a way just to dispatch off of a symbol type or a protocol? Because that's something that I sort of miss from the little bit of Haskell that I played around with, like the ability to create an algebraic data type and just start creating these functions based on that shape that you define. I really enjoyed that, and that's something that it would be fun to see something closer to in Clojure.
Okay. I'll repeat the question, and I'll summarize it because it was a long question. It's basically asking about dispatching off the type of the pattern, and that being a very natural way to do pattern matching if you've ever had a language to experience that. So the answer is sort of, in the sense that guard expressions, anything truthy or falsy, will work. So you absolutely can introspect on type and do things like that in your guard expression. So guard expressions can get very complex. They can call your user-defined functions that could have their own namespaces, and there's no limit. There's not an Erlang, the side effects are limited of what can be in a guard expression. With these macros, they're not. You could go off and call a database in a web service. You could do crazy things, right, in these guard expressions. And less crazy things, like introspecting on types and figuring it out. But syntactically, it's not maybe as clean as I think you're hoping for once you end up writing those expressions. So I still think there could be some benefit of bringing core type together with CoreMatch and defun. Other, maybe back there?
Yes, I'm a big fan of pattern matching, but at the end of the day, as much as we like to talk about it being declarative, it really doesn't reflect what we want to do with the order of its statements and the patterns that were defined before the one that we implemented. Right. So unlike something like maybe calling multiple dispatch, where you may have like an on
It's still sequential, right?
Think about what else is matched and how much going to be run. And do you know any alternatives or anything that ducks that question?
Yeah, I don't. I'll repeat the question, try to summarize it again. It was just a challenge to ultimately how declarative this style of pattern matching is, because it's still, order still matters here, and there's still a sequence that the patterns are going to be evaluated in one after the other. And it's something that's truly declarative. You think about being able to throw, like in a Prolog sense, throwing a bunch of facts against the wall, and just whatever's true is going to happen, whatever's false is going to happen, right? In the sense that order isn't, and something that's purely declarative, order doesn't matter, right? Even just saying that there's an order is putting some imperative structuring into it. So it's true that observation is absolutely true. It's not as declarative, but I think it's a step in that direction. The question, the final part of the question was, do I have any ideas about how we could get closer? And I don't, not at the moment. I haven't seen anything that gets us closer. I think it's possible with macros to get a lot closer and to have something that's more declarative and less sequential. I think the reason these macros are written in the way they are is the question that we had first, which is for performance. I think to make them more declarative would make them less performant as well. Maybe one more question, because I think we're out of time. In the back?
The question was actually related to that same thing. Is that can you match more than one statement? As in, is it just reading and it's just...
Yeah, the question was, can you match more than one statement? And the answer is no. Both of these macros are just matching the first one that matches, and the order does matter. It's in the order that you make the patterns. So that's it. We're out of time. If folks have questions, they can hang around afterwards.